Welcome to day 2 of the notes. Before we get started, let's review what we've talked about so far. And we've talked about how the periodic table helps us organize things and makes our life a lot easier once we know how to use it. The periodic table organizes and classifies elements based on various properties. One way it classifies it is basically if it's a metal or a non-metal. So metal, left-hand side of the periodic table, non-metal, right-hand side of the periodic table. Metals we know are going to lose electrons. Non-metals are going to gain electrons. So that's one way we classify, is basically whether they're going to lose or gain electrons. Another way we classify is by looking at the groups. Remember, groups go up and down. And this is going to tell us how many valence electrons they have. So we can classify it whether it's going to gain or lose, or how many it has. So example, group 1 has 1 electron. Group 2 has 2 electron, etc. Today we're going to talk about another way we classify stuff, and that's all about location, location, location. So not just whether that element's going to gain or lose an electron, or how many valence electrons it has, but where. Where are those electrons located? So how they do is they break it down into 4 main categories. And just like the other one, the noble gases, because they're so special, they get their own category almost every time. And they're special because they've maxed out. Their outer orbital, their valence electrons, is holding the maximum it can. All of the S's are filled and all of the P's are filled. We know S's can hold 2. We know P's can hold 6. And that's going to give us our 8 valence electrons. So 8 is great. Unless you're helium, then 2 is just fine. And because their outer shell is filled to capacity, they're inert. They don't react with anything because they don't need anybody. They have all the electrons they want. So they get their own special group. The next category are going to be your representative elements. And these are old school groups 1A and through 7A. New school, it's 1, 2, and then 13 through 17. And these are all the ones that are located in the S and P blocks. And they're not filled to capacity, because if they were, they'd be a noble gas. But that valence electron is located either in the S block or the P block. The third category is going to be your transition metals, and these are the ones that are hanging out in the D block. These are your D block elements. And then inner transition metal, these are your F block elements. And it's all about where, oh where is that electron? So whether they're all filled, so you got your noble gases, you've just got your representative, it's just the S or P, or you've got the transition where that valence electron's hanging out in the D block, or your inner transition where it's hanging out in the F block. That's the third way to categorize them. So we talked about how whether it's a metal or non-metal, you do not have this version of the periodic table of ions, but your periodic table does show this on yours. I believe the number's up here in the upper right-hand corner. But you can tell, hey, these are all group 1s. They have 1 electron. And they're going to want to lose it because they're metal. And when you lose an electron, you have a positive charge. So that's why these are all positive 1s. Here's group 2. They have 2 valence electrons, and they're metals, so they're going to want to lose them. And in that tug of war, if you're losing electrons, the protons are winning, so you're going to have a positive charge. Then we have a bunch of these weirdos over here, which we'll talk about in a minute. And then you get back to your nonmetals. So chlorine has 7 valence electrons, and we know our nonmetals gain. And in order to get that magic number 8, that chlorine just needs to gain 1 electron. So if it just gains 1 electron, the electrons are now winning in that tug of war, so it's going to have a -1 charge. And we'll get into these more, these charges here when we get into bonding next unit. But one thing I want you to notice is right here in your D block and your F block down here. We have some weird elements where they have options. So remember, S and P block, that's what we're going to focus on in Chem Honors, because those are very few exceptions. Your D block and your F block, these are filled of exceptions. So you can see a bunch here where there are options of how many electrons they're going to lose. And again, they're metals, so they're going to lose them. So why are there options? It's all about where the valence electrons hang out. And it could, you could see how it didn't fill this S block before it started filling the P block. It didn't fill the S block before it started filling the P block. That will give you one option. I don't remember which one it is. That's more AP Chem. If it decides to fill this S block first, it's going to have less than the P, and then you're going to have a different option. You don't need to memorize what these different option things are. You just need to know, hey, when I look at my periodic table, chromium has 2 options for these charges, and it's all because of those electrons. And that's good for us right now. All right. So again, we can classify whether they have, how many valence electrons they have. We look at the group number, that'll tell us valence electrons. Whether it's a metal or a nonmetal, that'll tell us if it's going to lose electrons or it's going to gain electrons. We can look at, is it in the S block, the P block, or if it's a noble gas, is it in the D block or the F block? That's going to tell us where those electrons are, which is going to be very important for our next unit when we get to bonding. So those are the 3 main ways we can use the periodic table to classify things. And that's the 3 main reasons why the periodic table looks the way that it does. So again, it all happened because we saw these repeating pattern of properties that it wasn't an exact, it wasn't every 3, it wasn't every 8, it was every once in a while. It happened periodically, which led to the whole periodic table. So what else can it tell us? I mean, this is what we've gone over so far. We've gone over alkali, alkaline, transition, just not too exciting metals. We didn't really talk about them. We talked about metalloids, aka semimetals. We talked about nonmetals, halogens, noble gases, the actinides, and the lanthanides. So we've covered all of that. And we've talked about group numbers and period numbers. Can this periodic table tell us anything else? The answer is yes. It can tell us a bunch of trends for a bunch of these properties we know about elements. So let's give an example of trends. the first trend we're going to talk about is atomic radius. And that's just, well, the radius of an atom from its nucleus to its outside. Now they use it, they calculate it by finding, the diatomic molecule of it, but radius, how big is that atom? So the first trend we see is with basically the size. As you go down the periodic table, you should notice it gets bigger. Ooh, that's not a good color. Let me try this again. So as we go down the periodic table, it gets bigger. And that should be pretty easy peasy to understand because, hey, we've got more floors in our hotel. So our building's going to be taller. So, yeah, the atom is going to get bigger as you go down a group. Now let's talk about as you go across. As you go across, you should notice it gets smaller. And that's where things get a little funky. You're not adding more floors to the hotel, so that makes sense, but you're adding more protons and you're adding more electrons as you go right. So why is it getting smaller? So as you go right, you've got this thing called shielding going on. It happens when you're going down, but it doesn't really affect it as much as when you're going across. It's because of shielding that the atom is getting smaller. So what's going on? As you're going across, you're getting more protons, which means that mama nucleus is getting more and more positive. It's becoming a stronger magnet. So because it's getting stronger, those electrons get pulled in closer. So that's going to affect the size. Now, shielding does not, oh, I said that wrong earlier. I'm sorry. As you go across, shielding isn't going to affect the size. As you go down, shielding does. Well, what is shielding? And, oops. What is shielding? I'll do this first. As you add more and more orbitals, so more and more levels, more and more floors, the electrons are going to repel each other. So not only are you adding more floors to the hotel, these guys want to get away from each other. So that's pushing it out even more. And because it's pushing it farther away, that nucleus doesn't even have as much of a hold on it anymore because it's getting pushed away. And again, we see this more as we're going down a group. So as you go down the group on the periodic table, the elements get bigger because one, you're adding another floor, and two, these electrons are pushing each other away. So again, as you go down, let me make sure I get it right this time, shielding also makes it get bigger. As you're going across, shielding doesn't really affect it because you're not adding electrons to a new level, so you're not getting that repulsion between the floors. So if you need to look at this a little bit more, hit pause now, stare at the notes there, otherwise I'm moving on. So if we were to graph it and graph the atomic number, so that's your number of protons and your number of electrons, compared to its size, you'll notice it goes, oops, it increases, and then you go to a new period and you're going across, then it gets smaller. Then you started a new period. So these here are all in the same group, which ties into the, as you go down the periodic table, these guys get bigger. But as you go across, these guys get smaller. Yes, there's a little bit where it increases here. That's, I bet you, right in here, I bet you if we were to break that down, those would be D and F elements, and then we got all the weirdos going on. So we don't have to worry about that. Again, I want you to know the general trend. On a test, if I said, hey, you've got boron and you've got chlorine, who's bigger? Who's got a larger radius? Just by looking at your periodic table, you should be able to tell me which one's bigger. And that's what we want you to get out of that. So again, here's the trend you might want to add to your periodic table. Again, as you go down, the radius increases because you're adding floors and you've got the shielding effect of them repelling each other. As you go right, it's going to get smaller because you're not adding floors, but you are adding protons, so your nucleus is getting stronger and it's going to pull those guys in tighter. It's going to hug them in tighter because it can. All right, so again, as you go down, it gets bigger. As you go across, it gets smaller. Another trend we can see from the periodic table involves ionization energy. So let's define that first. Ionization energy is how much energy you need to get rid of an electron. So to steal an electron, to take away an electron from, the valence orbital, the outer layer. And we go for the outer shells first because it's easier to steal an electron away from mama nucleus that is far away versus ones that are close. So where we see the highest ionization energy, or as we say in the biz, IE, is in the upper right corner of the periodic table, because it's going to be hardest to pull because they're so small. So you got mama nucleus here, and that electron is right by it. So it's held very tightly versus if it was something in the bottom right corner where you're on the 8th floor, way out here, mama nucleus doesn't have as great as a hold on it. So I like this because it kind of explains it. So remember, kids, the more electrons, the easier it is to lose or gain them. The more the electrons, the lower the ionization energy in general. So let's look at that trend. So again, as you go right, it's going to take more energy to take away an electron. As you go down, it's going to take less because, that electron is getting farther and farther away from mama nucleus, so it's really easy to snag it and take it away. So again, the farther away it is, the easier it is to grab. So if an element has a high ionization energy, it really doesn't want to lose any electrons. And if you think about it, this being one of the highest ionization energies, one, it's close to mama nucleus, and two, it has 7 valence electrons. It doesn't want to lose any, it just wants to gain 1. It is so close to perfection, it can almost taste it. So don't take away my electrons. I almost have what I need. All right, so, oops. So ionization energy, again, as you go down a group, it decreases. Because you're getting farther away, it's going to be easier to snag. As you go across a group, it's going to increase. So as you're going right, it's increasing because, one, you're getting more protons. So mama nucleus is getting stronger, and they're still on the same floor, so she can huddle them even closer to her easier. And those are the trends you want to memorize about ionization energy. So this chart here, nothing to write down, but take what you want to get out of this is taking the first electron away requires some energy. But then you want to take a second one, and it's going to take even more. So lithium, a group 1 element, it has 3 valence electrons. 2 on the first floor, 1 on the third floor. You want to take that first one away? That's not too bad. You want to go for that second one. Now it's going to put up a big fight because here it looks just like helium. It's got that noble gas. Its first floor is filled to capacity because that first floor can only hold 2. And then if you want to take the third one away, you're going to need even more energy. So you can kind of see that in the trends there. And the ones, you can see the noble gases take a lot. And you can say, hey, that's probably group 7. So it doesn't want to lose it. It wants to gain 1. Versus sodium, which I think is group 1. So it's like, yeah, here, take my electron, please. Doesn't require a lot of energy to take it because it's a metal. It wants to get rid of it. And you don't have to memorize these values. You just need to know the trend. If I say, hey, sodium versus argon, which one has a higher ionization energy? You should be able to tell me that. So again, you saw those big jumps. Big jumps, right? Yeah, big jumps right there. When you're trying to, oh wait, no, that wasn't the right one. Sorry, big jump here. There it is, that one. There's the big jump we're looking for. When you're trying to remove from the next, from an inner energy level or a full energy level. All of the S and P's are filled. So again, if we were to graph those ionization energies, you can see how it pops up. Oh, look at that. There's your noble gas, noble gas, noble gas, noble gas, noble gas. As you go down, it is a little bit easier because they're getting farther away. But these guys are all the way to the right of the table, so they're going to be hard that way. And they've got all 8 electrons. They don't want to lose them. Here, right here, here's your group 1 elements. You can see it decreases, not a lot, but it does decrease as you go down. Again, they only have 1 valence electron. They want to lose it, so they don't have much energy. You don't require much energy, ionization energy, to take them away. And then here, as you go across the period, you can see how as a trend it increases. Now what's up with this dip here? If we were to draw it out, let's see, lithium, so it's 1s2, lithium is 2s1, then let's see, hydrogen helium with beryllium is 2s2, boron is 2p1. So that's why it dips there, because you just need to steal one from that p orbital. The s orbital is full, so it's a little bit more to steal it, but the p orbital only has the one, so that's what makes it a little bit easier, because it's hanging out in the p. And then if you get to, let's see, if you get to boron, oh sorry, beryllium, boron again is why it dips. Carbon is going to be 2p2, so that's a little bit more. Nitrogen is 2p3, and then it dips at 2p4. And the reason why it dips is if you, let me get rid of some of this writing here. Hold on. If we draw it the other way, so here's your S, here's your P's. So we have hydrogen, helium, lithium. So it dips because that's easier to grab. Beryllium, boron, carbon. That dips because it's easier to grab. Nitrogen, oxygen, fluorine, and neon. Oh, sorry, that should have been, I forgot the 2s in there. Oh, but you get my point. You could see where it dipped and why if you draw out the electron configuration that way, the orbital notation. All right. Whew. So we've done radius. We've done ionization energy. Another trend is electronegativity. So let's start out with defining that. It's kind of the opposite of ionization energy. Ionization energy is how much energy it takes to remove an electron. Electronegativity is how much it wants to gain one. And because noble gases are complete, they don't want to gain any at all, we consider them that they have no electronegativity value. So, electronegativity, how much do you want to gain an electron? Now this one, there's no energy involved. It's either going to gain one or it doesn't. So we don't have like a measurement. We just give them a value between 0 and 4. That's the electronegativity scale. Again, metals in general have low electronegativity because they don't want to gain an electron. They want to lose it. That's what being a metal is. In general, nonmetals have high electronegativities because, well, that's the definition of nonmetal. They want to gain electrons. So they're going to have a high value, because a high value, a 4 means really wants to gain, and a 0 means, well, that's your noble gases. They don't want to do anything, whereas a 1 is a doesn't want to. Sorry about my horrible handwriting. All right, so it was just the electronegativity value was just this arbitrary number that this guy, Dr. Pauling, assigned to him. And he based it all on fluorine being the most electronegative and francium being the least. And if you look at their location on the periodic table, it should make sense. So fluorine, group 17, it has 7 valence electrons. It really just needs to gain 1. And that 1 is really, it's only, let's see, it's got 7. Let's see if I can draw here, sorry. Well, I'm trying to draw 7 on the second floor. So it's really close to mama nucleus, who's got that positive pull, which is also going to affect it attracting it. Versus, what did the note say? Francium is the least electronegative. Where did francium go? I'm not seeing francium on mine. I think I'm missing some elements. So I believe, if I remember correctly, francium should be right down there. So not only does it have one valence electron, it doesn't want to gain anymore. It wants to get rid of the one it has, but that one valence electron is located on, let's see, 1, 2, 3, 4, 5, on the 7th floor. So it's really far away from the pull of mama nucleus. So it's, yeah, don't give me any. I've got one, and will somebody please take it? It just wants to lose it. So you might see some, if it's got a high ionization energy, it probably has a low electronegativity. I think they're kind of like inversely related. And if it has a low ionization energy, it's going to have high electronegativity. So there's your trend. As you go right, it gets higher. As you go down, it gets lower-ish. And again, on the test, the questions would be like, hey, there's carbon and there's magnesium. Which one has a higher electronegativity? And you should be able to just look at your periodic table, see where they are, and know. So again, this is kind of like a pie, not a pie chart, a bar graph of electronegativity values. Francium has the least, fluorine has the most, noble gases have none. And again, the general trend is electronegativity increases as you go right, and it decreases as you go left-ish. So electronegativity as you go down, again, it's getting farther away. You've got that shielding going on. It just does not want another electron. As you go across, it increases. Mama nucleus is getting stronger because there's more protons. And it's getting closer to that magic number. Remember, 8 is great. Unless you're helium, then 2 will do. And so it's not going to want to lose electrons. It's going to want to gain them to get that magic number. And next unit, when we get into bond type, we can use electronegativities to help us predict what type of bond it's going to form. All right, so again, oxygen, more electronegative than sulfur. Where is oxygen? Let's see. Oh, oxygen is there. Group 17, period 2. Sulfur, group 17, period 3. So oxygen just got that one level of shielding. Sulfur has 2 levels of shielding. And that's going to pay, again, that shielding is these guys pushing, well, that's better there, pushing each other away, which is going to make it bigger. And because it's bigger, these electrons are farther away from mama nucleus. Again, the farther away they are, the less control or influence it has over the electrons. All right, so you should know the trends for electronegativity and why, the trends for ionization energy, atomic radius. We haven't talked about nuclear charge, and the trend for shielding. And that concludes the notes. Sorry I talked a little bit longer than I wanted to, but hopefully you've got this.